Hello everyone, welcome to this lecture of the course heat transfer. Today we will be discussing the second mode of heat transfer, that is convection, in details. Okay, so let us start this lecture. So earlier we have discussed what is convection. So it is the transfer of heat within a fluid by mixing of one portion of the fluid with another. And convection can be classified in two, that is the natural convection and forced convection. Now, before going into the details of this module convection, we need to first revise our basic concept of fluid mechanics, because the basic concept of fluid mechanics need to be very much clear to us before going into the details of this course or of this lecture, convection. So let us start with the basic concept of the fluid mechanics. Now, if we want to define the term fluid, in that case, how it will be? How we will define the term fluid? If someone says that fluid is a substance which flows, then it is an in general definition of the fluid. But how to define the fluid technically? In this standard, how we will define that term fluid? So, if we want to define the term fluid appropriately, then we can say that all matter, these are consists of only two states, fluid and solid. Now, a solid can resist a shear stress by a static deformation, but a fluid cannot. But any shear stress applied to a fluid, it may be negligibly small, but it will result in motion of the fluid. That means the fluid moves and deforms continuously as long as the shear stress is applied. So from this concept we can define that a fluid is a substance that deforms continuously when subjected to a shear stress, however small the shear stress may be. Okay, so this is the appropriate type of definition of the term fluid. So that is what a fluid is: a substance which deforms continuously when subjected to a shear stress or tangential stress, however small the shear stress may be. Okay, so a fluid may be either a liquid or a gas. Now, how to differentiate between a solid and a fluid, or maybe a liquid and a gas, that is the part of fluid. So these are some basic concepts of the fluid mechanics that I am discussing here. So how to differentiate between a solid and a fluid? Earlier we have studied in our school level that the molecules of a solid, these are closely packed together than those of a fluid. That means the attractive forces between the molecules of a solid, these are so large that the solid tends to retain its original shape. However, the fluids cannot retain its shape because the attractive forces in between the molecules of the fluid, these are smaller. So that is the thing that is familiar to us. But what may be some other in-depth difference between the solid and the fluid? Now, the fundamental difference between a fluid and a solid, it lies in the response to a shear stress of the respective materials. That means what? For a solid, the strain is a function of the applied stress, provided that the elastic limit is not exceeded. But for a fluid, the rate of strain, it is proportional to the applied stress. So this is the fundamental difference between a fluid and a solid in terms of the shear stress. Again, the strain in a solid, it is independent of the time over which the force is applied. And if the elastic limit is not exceeded, then the deformation appears when the force is removed. So that means what? A fluid continues to flow as long as the force is applied and will not recover its original form when the force is removed. Okay, so these are the basic difference in between the solid and a fluid. Now, how to differentiate between the liquid and gases, that is the type of fluid. So the difference between the two classes of fluid, that is liquid and gas, it lies how they behave with their cohesive forces. So what happens? A liquid being composed of relatively closely packed molecules than the gases, there the cohesive forces are strong. So the liquid tends to retain its volume and it will form a free surface in a gravitational field. But what happens in case of a gas? In case of a gas, since the gaseous molecules, these are widely spaced with negligible cohesive forces. That means the cohesive forces, these are smaller compared to the compared to the liquid. So what happens, in case of gaseous molecules, the cohesive forces are smaller compared to the liquids. So what happens, a gas or gaseous molecules, these are free to expand until it encounters confining walls. So a gas has no definite volume, and when left to itself without confinement, in that case a gas forms an atmosphere which is essentially hydrostatic. So these are the things we have already studied in our basic concept of the fluid mechanics. Now there are different fluid properties that also we have studied, like density, then specific weight, specific volume, specific gravity. All these basic fluid properties we have studied there. So I am not going into details for all these things. Now there is a most important fluid property that we have studied earlier, that is known as viscosity. So what is this viscosity? How to define this term viscosity? So a viscosity may be defined as the property of a fluid which determines its resistance to shearing stresses. Okay. So it is actually a measure of the internal fluid friction which causes resistance to flow. So this is the proper definition of the viscosity. It is the property of a fluid which determines its resistance to the shearing stresses applied. And now the resistance depends on the rate of deformation. Now in case of this viscosity, there was one law that we have studied earlier, which is known as the Newton's law of viscosity. So what was that Newton's law of viscosity? The Newton's law of viscosity, it is actually, it is the statement, or from the formula, what is known as, it is the shear stress is proportional to the rate of shear strain or shear deformation. Now if the shear stress is denoted by tau, and if you use the velocity, and in that case we can say that the shear stress tau, it is proportional to the rate of shear strain, that is du dy. So y is the distance in between the two different fluid layers considered. So tau is proportional to du dy, that is shear stress is proportional to the rate of shear strain. Now this formula or Newton's law of viscosity, it can be represented as tau equals to mu du dy. So what is this mu? This mu, it is the constant of proportionality, and it is known as the coefficient of dynamic viscosity. It is du dy, it is the rate of shear stress or rate of shear deformation. It is also known as the velocity gradient. So, and this mu, it is the coefficient of dynamic viscosity. Now this viscosity, it is primarily due to cohesion and the molecular momentum exchange between the fluid layers. and when the flow of the fluid happens, these effects appear as shearing stresses between the moving layers of the fluid. So that means what? The causes of viscosity, these are basically two. One is the intermolecular forces of attraction, that is the cohesive forces, and the molecular momentum transfer or the molecular momentum exchange between the fluid layers. Now, there are some classification of the fluid. That is, one is the ideal fluid and another is the real fluid. So what is this ideal fluid and real fluid? An ideal fluid is one which has no viscosity and surface tension and it is incompressible. But in reality, no such ideal fluid exists in nature. But fluids which have low viscosity such as water and air can be treated as ideal fluids under certain conditions. And what happens in case of real fluid? A real fluid is one which has viscosity, surface tension and compressibility in addition to the density. So this is the basic difference in between the ideal and real fluid. In case of the ideal fluid, it is considered that it has no viscosity, or in real life it is having very low amount of viscosity. But in case of real fluid, it experiences a significant amount of viscosity. So from the diagram given here, in case of the viscosity of liquid, four different things are given. The viscosity, one is water, another is milk, then oil and the egg yolk. So in case of water, as we have discussed, that water and air, these are having low viscosity, then these are considered as almost ideal fluid. So from their basic concept of the viscosity, we can see here from that how they behave in terms of their low or medium viscosity. Now there are more number of classification of fluid flow. So what are those? Like steady and unsteady flow, in uniform and non-uniform flow, then laminar and turbulent flow, next compressible and incompressible flow, then rotational, irrotational flow, then one-dimensional, two-dimensional and three-dimensional flow. So these are different classifications of fluid flow. So let us discuss in brief some of those different classification of fluid flow, like what is steady and unsteady flow. So when the fluid properties does not change with respect to time, then it is known as the steady flow. And when the fluid properties like velocity, pressure, it changes or it varies with respect to time, then it is known as the unsteady flow. Next, the laminar and turbulent flow. So what are those, the laminar and turbulent flow? So in case of the laminar flow, the fluid layers or the fluid particles, these are parallel to each other and the fluid layers move along a streamline. So this is the laminar flow in brief. And in case of the turbulent flow, the fluid layers are not parallel to each other. They mixes with each other and the movement is in a zigzag way. Now, how to differentiate and what is that particular thing or particular parameter based on which we can say that this flow is laminar or turbulent. So for that, there is an important dimensionless number that is known as the Reynolds number. So what is this Reynolds number? So based on the experiment of the scientist Osborne Reynolds, and based on his experiment, we have got the existence of these different flows, that is laminar and turbulent flows. So what is this actually, this Reynolds number? It is the ratio of the inertia force to the viscous force, this Reynolds number. So, and in case of a pipe flow or closed conduit, in that case scientist Reynolds, he has seen that the Reynolds number or the nature of the flow, it depends upon some factors. So what are those factors? One is the diameter of the pipe, next is the density of the fluid, next is the viscosity of the liquid, and the velocity of the flow. And if we combine all these factors, then we are getting a non-dimensional quantity, that is Re, that is the Reynolds number. It is equals to rho u d by mu. So rho is the density of the liquid, u is the velocity of the liquid, d is the diameter of the pipe, and in general case this d is actually represented by the L, which is the characteristic length, and this mu, it is the dynamic viscosity of the fluid. It can again be represented as ud by nu. So nu is actually mu by rho, that is dynamic viscosity by density. So this is another representation, ud or ul by nu. So in that case nu, it is the kinematic viscosity, that is dynamic viscosity mu divided by rho density. So now what is the value of this Reynolds number based on which we can say that the flow is laminar or turbulent? Reynolds has seen that when this Reynolds number, that is rho Vd by or rho ud by mu, if it is less than 2000 or in some cases 2200, then the flow is called, it is laminar or viscous. Now when this Reynolds number, it is in between 2000 or 2200 up to 4000, in that case it is the transition zone, or it can be called, it is the unpredictable zone of that fluid. That means there the fluid is neither laminar, fully laminar, or fully turbulent. But when this Reynolds number is greater than 4000, in that case the flow is fully turbulent in case of a closed conduit or pipe. Okay, so this is the value of the Reynolds number based on which in case of a closed pipe we can say that the flow is either laminar or turbulent. But when the fluid flows over a flat surface, in that case what is the value of this Reynolds number? That thing we have studied in our boundary layer theory concept in fluid mechanics. So and this boundary layer theory concept, it will be discussed in details in the next lecture. Now in that case, when a fluid is flowing over a flat surface, in that case it is seen that when the value of the Reynolds number is less than 3.2 into 10 to the power 5, then it is the lower critical Reynolds number, and below this value the fluid flow, it is called as it is of laminar nature, it is the laminar fluid. Next, from 3.2 into 10 to the power 5 up to 5 into 10 to the power 5, in this range the fluid flow is unpredictable or the transition zone. And when the value of the Reynolds number is greater than 5 into 10 to the power 5, in case of a flat surface, then the fluid flow, it is of turbulent nature. So all these things regarding this boundary layer theory concept, it will be discussed in details in the next lecture. Now this Reynolds number, it is having its upper critical and lower critical values. So it also depends on different factors like the initial turbulence in the flow, then shape of that pipe or the shape of the surface, its roughness maybe. So all these things, these are the different factors based on which the critical values of the Reynolds number changes. So there is a lower critical Reynolds number and then upper critical Reynolds number. So the lower critical Reynolds number, it is actually 1 in case of a sphere, and it is actually 50 in case of open channels, and it is 1000 in case of parallel plates. So till now we have discussed in brief the difference in between the laminar and turbulent flow. Next, there is another important classification of fluid flow, that is compressible and incompressible flow. So what is this compressible and incompressible flow? So in case of incompressible flow, the density of the fluid, it remains constant when the pressure changes. So this is the incompressible flow. But in case of compressible flow, what happens? Then the fluid density, it varies when the pressure changes. Now, as the in case of the incompressible flow, as the fluid velocity, sorry, if the fluid density remains constant, or fluid density remains constant when the pressure changes. That's why the fluid density is considered as uniform or constant, because the change is very much negligible when the pressure changes in case of the incompressible flow. As the change is very much negligible, that's why the density is considered as constant in case of incompressible flow. And in case of compressible flow, the density changes significantly when the pressure changes. And that part, that is the compressible flow part, that comes under the gas dynamics part. In that case also, there is one important dimensionless term we will study in future, that is known as the Mach number. So these were some basic review of some basic concept of the fluid mechanics. So till now we have discussed the appropriate definition of the fluid, then the difference in between the solid and the fluid, the liquid and the gas, then the Newton's law of viscosity, what is viscosity, then the Newton's law of viscosity. Now there is one thing, that the fluid which obeys this Newton's law of viscosity, these are known as Newtonian fluid, and the fluids which do not obey this Newton's law of viscosity, which is shear stress is proportional to rate of shear strain, the fluids which do not obey this Newton's law of viscosity, these are known as the non-Newtonian fluid. And this viscosity of a liquid, it decreases with temperature, but the viscosity of a gas, it increases with the temperature. Now this mu, it is the dynamic viscosity, and mu by rho, that is the mu dynamic viscosity by density, it is known as kinematic viscosity. Next, what is ideal and real fluid? These things we have discussed. Next, different classifications of fluid flow, that is we have discussed, and how to differentiate in between the laminar and turbulent flow based on the Reynolds number and its critical value in case of a pipe or a free surface or a flat surface, that those values we have discussed in brief till now. Let us move to the next page. So what is the objectives of convection analysis? So what happens then in case of the convection? The main purpose of this convection or the convective heat transfer analysis, it is to determine the flow field, then the temperature field in fluid, and the heat transfer coefficient, that is small h. So earlier we have studied the Newton's law of cooling in case of the convection heat transfer. There we have seen the Newton's law of cooling, that is Q equals to HA, and the temperature difference. So this small h, it was the convective heat transfer coefficient. So these are the main purpose of the convective heat transfer analysis. It is to determine the flow field, the temperature field, and the heat transfer coefficient. Now, how do we determine, or how to determine this convective heat transfer coefficient? Let us consider the process of convective cooling as we pass a cool fluid past a heated wall. So in that case, the process is described by Newton's law of cooling, and the formula it is known to us Q equals to HA multiplied by Ts minus T alpha. Now in this diagram, that is the concept of the boundary layer, the velocity boundary layer and thermal boundary layer. These are given here. The boundary profiles, these are given. Now this capital U that is in the left side of this diagram, it is the free stream velocity. Now near any wall, a fluid is subjected to the no slip condition. So what is this no slip condition? If we consider a flow of a fluid over any solid surface, like in this diagram, the fluid is flowing over the solid surface, that is the black surface here. The fluid is flowing over this black flat surface. Now, from the all different experimental observation, it is seen that a fluid in motion, it comes to a complete stop at the solid surface, and there it assumes or it gains zero velocity relative to the surface. That means there is no relative tangential velocity between the fluid and the solid boundary at their contact points. So at these contact points, when there is no relative tangential velocity between the fluid and the solid boundary, then it is known as the no slip boundary condition. This no slip boundary condition here we have considered. That means there is a stagnant sublayer, that is there is no tangential relative velocity. Since there is no fluid motion in this layer, so that means what? The heat transfer, it is by conduction in this region. Now above this sublayer is a region where viscous forces retard the fluid motion. Now in this region some convection may occur, but the conduction may well predominate. So that means a careful analysis of this region, it will allow us to use our conductive analysis in analyzing the heat transfer. So this is the basis of our convective theory. So from this concept of the boundary layer concept, we can ultimately determine the basic or the basis of our convective theory, the heat transfer through the convection analysis. Now at the wall, the convective heat transfer rate, it can be expressed as the heat flux. So that means Q convection, this is equals to minus Kf dt dy at y equals to 0, this is equals to H multiplied by the temperature difference. So that means from this equation we will get the value of convective heat transfer coefficient H equals to minus Kf dt dy at y equals to 0 divided by the temperature difference, where this temperature difference dt del t del y at y equals to 0, it depends on the whole fluid motion, and both fluid flow and heat transfer equations are needed. So that means what? This expression, it shows us that in order to determine this convective heat transfer coefficient, that is small h, we need to first determine the temperature distribution in the thin fluid layer that coats the wall. So that is the thing that we need to determine. And what is the difference, or what is the classification of this convective flow, the convection heat transfer? Earlier it is discussed that the convection or convective heat transfer, it can occur in two ways. One is the free or natural convection. It is induced by the buoyancy forces, and this, what is the buoyancy force, it is already studied in the fluid mechanics. And another is the forced convection, that is induced by the external means. So this convective heat transfer, it can occur in two different ways. One is the natural convection and another is the forced convection. Now it may occur with phase change, that is boiling or condensation. Now this thing, that is boiling or condensation, it will be discussed in the later classes, the later lectures. Now this convective fluid is extremely diverse. There are several parameters involved, like fluid properties, geometry, nature of flow, phases, etc. in case of this convective heat transfer. And systematic approach is required. Next, it identify parameters governing the flow and group them into meaningful non-dimensionless numbers and need to understand the physics behind each phenomenon. So these are the things that we need to carefully examine. There are common classification here in this convective heat transfer. Number A is based on geometry. One is the external flow and another is the internal flow. Next, number B is based on driving mechanism. Natural convection or forced convection, or it may be the mixed convection. Number C is the based on number of phases, maybe single phase or multiple phase. And last, number D, it is the based on nature of flow, it may be laminar or turbulent. So all these things, these different classification based on geometry or driving mechanism or number of phases or based on the nature of flow, all these things will be discussed in the later classes. Now this is a table that gives us some typical values of this convective heat transfer coefficient. The unit is already known to us, it is watt per meter square Kelvin or watt per meter square degree centigrade. Now in case of free convection, if it is gas, then the value of H is in the range of 2 to 25, and if it is liquid, then the value ranges within 50 to 100. Next, in case of forced convection, in case of gases, the value of H lies within 25 to 250, and in case of liquid, it is 50 to 20,000. And in case of boiling or condensation, the value of this convective heat transfer coefficient, it lies within 2500 to 1 lakh. Now, how to solve a convection problem? So there are different parameters or different assumptions that we need to consider. We need to solve governing equations along with boundary conditions. Now, what are these governing equations? So these are some basic governing equations in case of the fluid mechanics. That is, number one is conservation of mass, number two is conservation of momentum, and number three is conservation of energy. It's conservation of mass, momentum, and energy. These are the three different governing equations. Now in case of any conduction problem that we have discussed earlier, only number 3, that is the conservation of energy, is needed to be solved. So that means only few parameters were involved in those cases in case of the conduction problems. But in case of the convection, all the governing equations we need to take into considerations. It means the conservation of mass, momentum, and energy, all these things will be taken into account. That means a very large number of parameters can be involved, and that's why the solving of the numericals, it will be much more complicated in case of this convective heat transfer. So this is the end for this lecture. Today we have discussed the basic review of the fluid mechanics and some basic introduction of the convection heat transfer. So in the next lecture we will be discussing the boundary layer concept, and based on that we will try to derive its associated equations, and based on that we will try to solve some numericals. So this is the end for this lecture.